It basically manufacture metal components like a craftsman would, right? What we need now is really fast manufacturing. We need distributed manufacturing. We need to be able to be very responsive, not to just market forces, but also to the things that happen in the world. We want to be able to pretty much in a very short amount of time go from thinking of an idea to manufacturing it.
And it's completely autonomous.
Yeah.
That's incredible.
We're here in Bentonville, Arkansas, and today we have brand new aircraft, we have spacecraft, EVs, we have AI-driven robotics, and so much more. This is UpSummit 2025. Welcome to UpSummit 2025. Today we're sitting down with Machina Labs. We'll jump in a little bit. First, I'd like to introduce my co-host, Tyler Flagg, good friends for a long time, founder of the flying company, putting aircraft owners and operators with pilots, creating a marketplace for that. Start of the show today, though, is Ed. Ed, you've done a lot here in the past few years. Why don't you give us a rundown? Explain it to me like I'm five, layman's term. What is this?
Yeah, so this is a system we call RoboCraftsman. It basically manufacture metal components like a craftsman would, right? Doesn't require any specific tooling that are specific to the geometry, the type of part you're trying to manufacture. Similar to how a human craftsman can pick up a tool, get to work on a metal, kind of go through a sequence of operations to make a metal product, be it a car panel or an aircraft panel. Figure out the steps and it will make that part for you without any specific tooling, any specific machinery that is designed for that specific part. So you can get your part like in a matter of hours after your design is done.
So we'll jump into the little technical things as we get towards the end. How did you get to this point? I mean, this is a massive machine. This is a massive operation. It's mobile. You just brought it here. How have you gotten to this point? What's kind of been the evolution?
Yeah, so I think it started from the vision, right? Like, what do we want to actually build? Manufacturing has been kind of the same for the past 100 years, right? The same technology that made like Model T, right? It's making Model S and Model 3 now, right? It's the same way of forming, sheet metal panels for the vehicle that has existed for the past 100 years. So we want to rethink that. Why do we want to rethink that? Is because the environment has changed. What we need now is really fast manufacturing. We need distributed manufacturing. We need to be able to be very responsive, not to just market forces, but also to the things that happen in the world, be it war, be it disasters. We want to be able to pretty much in a very short amount of time go from thinking of an idea to manufacturing it. So started from there. So it was like, okay, we want to make a system that's super fast, super agile with manufacturing. What does it need to look like, right? And we got the cue from humans, how humans are super agile. We call it RoboCraftsman because it's modeled after how a human operates, right? Can pick up tools, do different types of operation, be very nimble and agile with what it does. So we said, okay, we need robotic arms, right? We need something that has the same kinematic dexterity of human, can pick up different tools the same way human does. So that landed on robotic arms. But then the piece that kind of like gives it the intelligence is the AI piece. That's the software, right? To replicate what's happened in the mind of the craftsman, right? What sequence of operations do I need to go through? What process parameters do I need to use, right? And that's where the AI and the advanced software piece comes into play. But if you're making things fast, then we want to also make sure the factory is set up fast, right? So the system has to be portable, right? So that you can actually go into a new location in any warehouse, as long as you can have power. You have a system that opens up, gets ready for manufacturing within hours. So these systems actually turn into 2 containers. You can ship them on any regular means of transport, get into a location, connect them to power. They open up like a transformer, like a butterfly, start getting, going through their calibration routine, and then they can make parts in hours after they land into a location, right? So the vision was there, but we did multiple iterations on the product until we got here. But the vision since the beginning was fast manufacturing, not only in making the parts, but also in setting up the factory, right? And that's what, kind of defines what the type of decisions we made along the way.
This is incredible. It's running real time, creating a 3D structure of a face that you scanned a while ago. How fast is this going relative to how fast these machines can go, though? I know you slowed it a bit down.
No, we're pretty actually not even close to how fast these things can go, right? These robots can move around like 1 meter a second. So think about—
1 meter a second?
Yeah, so in 1 second you're going 3 foot, right? So we really slowed it down. Just so that people can see, and it doesn't also look scary, right? When they're manufacturing. But yeah, I mean, we're nowhere close limitations of how fast we go. There's some engineering improvements we need to go to even go faster than that. But right now we are basically probably like 1/5, 1/6 of what it can go.
So we were both in the Air Force. Obviously, you guys started your business development roadmap with the DoD, so we might as well start there as well. Can you talk to us a little bit about Air Force Research Laboratory and some of the other case studies y'all have done with the military?
Absolutely. Yeah, I think our first kind of like very natural shoe-in fit was, helping our military with mission readiness, right? When an aircraft gets damaged today, or, any weapon system that we have probably the most variety of weapon systems compared to any country that we're maintaining. Some of these are from manufactured in the 1950s, 1940s. So we're maintaining this very kind of diverse set of systems. And when they get damaged, some of these components, the OEM doesn't exist anymore, so we can't really remanufacture them easily. So very easy, kind of high impact area for us is just to work with military on sustainment. A landing gear door of a C-130, when it gets damaged, right now it's 4-year lead time because they have to go find a vendor, make toolings for it. And by the time we go through all the paperwork for DLA, that's 4 years, right? With us, it's hours and after the design, and the total time is probably just a few days before we can get to a new part. So that was the first area. We deployed a system to Warner Robins. We are working with other depots. We're also even thinking about right now with Special Forces to get even closer to the front line, right? Closer to the theater, especially with Pacific as the logistic challenges are kind of like bigger in that area, being able to immediately put a facility near the theater and start doing manufacturing it gives us a huge advantage.
Just given how small the footprint is, like being able to have it forward deployed in various locations.
Well, and y'all have a very specific use case at Ramstein Air Base, I believe, with the C-130 that was grounded for a long time, for exactly as you said, a gear door.
Yeah.
What happened there?
Yeah, landing gear door was one of them. I think the C-130 actually you're talking about it got damaged in a hurricane, right? A piece of wood went in through one of the skin panels. They couldn't pressurize the cabin anymore. And the traditional route to get that aircraft panel was like months, if not, up to a year. With us, we got the design. I think the same day we manufactured the first component. We did multiple iterations on it, but within the span of like few days, you get to the final product, final part that you can kind of send and do a fit up on an aircraft and
just strap it on the airplane and you're back to flying again. So from a sustainability perspective, that's honestly incredible. It's an incredible capability. I feel like especially as a society, we have less skilled people who are able to work with metal. You get the same results and a consistent result time after time.
Absolutely.
And then, so obviously you have the support to the United States, Department of Defense, but then what about to our allies? You had mentioned earlier off camera about our allies and the support that we can give to them.
Yeah, I think, we're fortunate that, our country, is oceans away from most of the conflicts, right? So a lot of conflicts that we have are with the, we're doing it with our allies, right? Being it in, Europe or being it in Middle East or in the Pacific. So one of the main things that kind of gives us an asymmetric advantage is that enabling our allies to manufacture, right? We're fighting war with folks in Ukraine. There are a lot of, great talent in that country, but we need to get them, we need to enable them to manufacture parts. And so one of the things we really thought about early on was like portability of the system and setting up a facility fast, in a friendly country near the theater. So that's something also we're thinking about, being able to set up a facility in less than a month to manufacture, defense articles with the help of the allies. That's definitely something that we're working with.
So we've talked about traditional aircraft manufacturing, right? We've got aluminum up there. I know that y'all have gone up to 1/4 inch steel, but there's some, like this SR-71 behind, right? That was made of titanium, and the tooling and making that was an incredibly complex process, and y'all are working with that. So talk to me a little bit about space, hypersonic, what you're doing with Lockheed Martin that nobody else can do.
Yeah, so no, that's a great point. I think a lot of kind of weapon systems, especially advanced ones, they're in these very harsh conditions. For example, we're talking about hypersonics, the temperatures are pretty high. Right. So that means you need to use alloys that can take these harsh conditions, right? So what does that mean? If the alloy can take a harsh condition, it means that it's also probably very hard to manufacture. Right. Because how do you shape it? How do you form it? It's supposed to actually resist any kind of deformation. It's supposed to be strong. So one of the things that we enable with our process is forming of these hard-to-form alloys. Think about nickel-based alloys. Think about titanium alloys. These are alloys that are traditional manufacturing has a very hard time processing them. With us, because we have more granular control over the deformation, we can actually push these alloys to the limit and kind of form them and not get to fracture or a failure, right? So that what does it means is that it opens up applications like hypersonic, where you want these high temperature, strong alloys. So we're working with the primes on that area. But also, traditional alloys, like you said, aluminum and steel, a lot of traditional widely used weapon systems and missiles and UAVs are still built out of those. So we're also working with them on making those processes more agile. One of the primes that we're working with, we looked at their traditional process. Compared to that, we are 4 or 5 times faster to get to the first article, right? So even in the traditional process, we give them a huge advantage.
And how long did that SR-71 take to make roughly?
Yeah, I think we went from design all the way to forming and then welding less than a month.
Wow.
Yeah.
That's wild.
That's incredible. And so we talked about alloys, these high temperature capabilities. So not only do you have the capability of sustainment for these old 1950s, 1960s airplanes that we're still flying, but then also rapid development, design, and testing of the latest and greatest thing that's on the market. That's like quite the gap in manufacturing that nobody else can really do.
Yeah, no, both, just do the past, kind of support the past weapon system, make new weapon systems faster, and then, distribute the manufacturing of it. So we're not relying on one location, right? A lot of people don't know this, but a lot of our weapon system rely on suppliers, a single supplier out of one location.
Right.
And if that supplier gets compromised, that weapon system.
It's a vulnerability that we have as a country that this opens up the door to solve.
Yeah, exactly.
So I'm a lot of people here don't know, I'm a bit of a gearhead car guy. And so let's shift a little bit to the automotive space. Obviously things aren't quite as expensive as they are in the aerospace or division, but y'all have an upcoming announcement with an OEM.
Yes.
You want to talk about that a little bit? I know that it hasn't been announced yet, but by the time this comes out.
But you guys get a sneak peek. So tomorrow we're going to announce that. It's our first kind of widespread, kind of large application that we're going to have with the commercial customer. That's something actually where I come from and what I'm excited about. I used to be a hobby kind of hot rod maker, making panels for old vehicles, 1930s Fords.
Yeah.
So, and car making used to be about self-expression, right?
Yeah.
Before we had these mass-producible cars, before Ford said, you can have any car you want as long as it's black.
Yep.
Before that, it was actually active, artistic expression, making these nice-looking, fancy cars that was would tell people who you are. Obviously, you had to be rich to do that, and mass production, and Ford kind of brought cars accessible to everybody. But now I think with our technology, we can combine the both of them, right? We can be expressive again, but also be mass producible, right? So what we're doing with the announcement we're going to have tomorrow with Toyota is kind of bringing that concept back. You as a customer can go to a website, the Toyota website, and say, hey, I want this fender, and I want this quarter panel, and I want this, roof panel, and I actually want to put my favorite sports team. I want to form it and emboss it in the tailgate of my truck, right? And get the car serial number 101 just for you at a mass producible prices. I think that would be a new category. We had autonomous, we had electric, and I think we can potentially have expressive custom cars at mass scale.
And so from order to delivery of that custom piece for that car, what are y'all expecting for that?
We'd have to finalize the detail, but a panel right now can be customized in a matter of minutes, right? So we go from a tailgate, and we have a Toyota Tundra here. The tailgate of that was customized by our technology. It takes 20 minutes to customize it.
Wow, that's insane.
And so not only do we have modern OEMs, and that's really exciting for just the automotive industry kind of moving forward, but we also have classic cars, right? You get a car that there weren't that many produced, there's not that many left. Obviously the tooling is not there anymore. And it used to be, you'd have to have these artisans come in and try to get it as close as possible, where you have the ability to get perfect and extremely consistent. If somebody were to do that, say that somebody's working on an old Ferrari and they're like, I need this quarter panel. Can they come to you and get that made?
Yeah, soon. Not yet, but soon. I always say the same thing. One of my favorite cars is SL300.
Yeah.
I was like, somebody needs to remake that.
Right.
Why is that not available anymore?
Right.
But yeah, I think the future we're imagining is that anybody who wants to make metal structures, especially sheet metals, can go to a website, Machina Labs website, upload their design, get guided through how they can make it manufacturable, and say, okay, I want like 20 of these in this location, and the right facility that's nearby gets programmed to manufacture those panels and send it to them in a matter of days. You're starting obviously with Toyota and big OEMs that share that vision because we're not expert in automotive, so we want to partner there. But eventually I would love this to be available for anybody. The goal, if you ask our folks in our company, the main reason they're working here is that kind of democratization idea. Before, if I graduated from school, the only way I could make an impact on a hardware product was go work for Hondas of the world, Toyotas of the world, SpaceX's of the world. Now it's no, you can actually make the thing that you want, and it's going to be cost effective, and you don't have to build a factory, right? So that's the future we want to be in.
Yeah, so for automotive, that's incredible. I'm a big GA guy, general aviation guy, and so a lot of these airplanes we're flying are from the 1950s, 1960s, 1970s, and finding parts for those can be hard, and when you do, they're incredibly expensive. And we're looking at junkyards, and we're trying to find it however we can to keep these airplanes alive. This, again, another application of just a way to keep the industry alive.
Yeah, bringing metal birds back, right? And one of the work that we were doing, you mentioned that, one of the work we were doing, we're going to talk about it tomorrow. There's this B-17 that Air Force has. It's like a historic bomber, and they're trying to restore it. Most of the panels are very hard to make, so we're helping to kind of restore that aircraft, something that was practically not really possible before us.
Yeah, we have a beautiful P-38 at the end of the runway. I don't know if you saw it or not, but Glacier Girls, I don't know if you're familiar with that. The P-38s that were in Greenland, and they were they melted into a glacier. They got rescued and brought out and completely restored.
That's
Having
amazing.
a technology like this would completely change the restoration game plan. And there's a lot of money in that as well, and a lot of demand for that. I feel like this has the opportunity to disrupt so many industries.
Oh, I'm glad you think that way. We think so, for sure.
Right.
And how many of these units do you actually have deployed?
So we have operational right now. We have, I think this is serial number 16. So we have 17 of these operational. Then there's another one. We're planning to get to next year to 5 a year. We're going to produce, and the following year 15 a year, because we're actually going into our third facility. So we have 2 facilities right now, 120,000 square foot in Los Angeles. We are opening up our third facility. It's going to be somewhere from 200,000 to 500,000 square feet, specifically for the missile products, UAV products that we talked about. And that's going to have 50 of them, and we're going to need to tool that facility up in the next 4 years. So we need to get to 10 to 15
so I assume you're going to be increasing your headcount here pretty soon, if you haven't already started.
You're at that 70 right now, planning to get above 200 in the next couple of years.
Wow. So we've talked a lot about the application capabilities. Let's talk a little bit about the machines. These machines are pretty impressive. One of the things that you have two end effectors, I think they're called, end effectors.
That's right.
That are touching and putting pressure against each other to deform it. And depending upon the shape and the pressure you put in, you can get incredible capabilities out of it. One of the things that really impresses me is how the machine has the capability of swapping out heads to get different effects. I was talking to one of your guys earlier. He said that for certain alloys, you can attach a heating element so you can heat the structure. And then in some of your facilities, you're actually having these machines put the alloy up, brace it, and it's completely autonomous.
Yeah.
That's incredible.
Yeah, no, I think, we call it RoboCraftsman for exactly that reason, because we started from sheet forming because sheet forming was this big pain point, largest metal processing sector that didn't really have an agile solution.
Right.
As we talked about planes, cars, it's really hard to make sheet panel formed, compound curvature formed sheet metal panels. But the RoboCraftsman, the goal behind it was that it can do different types of operations, right? Like a true human craftsman, can do this process, which is almost like pottery with metal. I think that's how I describe it. It's like you have 2 fingers and you're deforming and shaping a piece of metal. It's just the forces are much higher than pottery. But after that, you can just drop that tool, pick up a trimmer, trim it, drop it, pick up a scanner, scan it. You're working on forging, using a heat to kind of deform the metal, bending, hemming, and heat treatment process. So we constantly want to add it because it's really, the idea is that you have a facility, you put 200, 300 of these, and then you can kind of program all of them to do the same thing to get throughput, or you start programming each of them to do different things to get variety. So now you can get the good mix of both high mix and high volume.
Yeah, and one of the things that's really fascinating about this is if you were to develop the traditional system of going through a mold, a lot of time, a lot of effort, and you have to go through several series of mold before you finally get to the mold. Once you get there, now you can stamp out the parts pretty quick. Where do you see that economies of scale shifting between going with a system like this or going with a traditional mold system?
So today, based on the current numbers that we have today, it's in thousands.
In the thousands?
Yeah, tens of thousands, right?
Wait, today it's in the tens of thousands before you run?
Because if you think about it, so when you want to compare the two solutions, you have to do, okay, how much it takes to make a mold. So there's two ways to kind of figure out the break-even point: time and then cost. So when you talk about time, you need to be, okay, how long it takes for me to make a mold? And during that time, how many parts I can make, because I can start making parts with this immediately after design does. With that, you have to wait at least 3 months to make the mold. And then with the same investment in mold and equipment, as stamping equipment, how many of these can you put in parallel, right? So you have to think about like this, okay, what is the equivalent investment? How many of these I can get? And then with that, you're looking at a few thousand, all right? So if you have a facility that you fundamentally start thinking about this, okay, I'm not gonna do stamping, I'm gonna do this, you can actually be pretty cost effective. And then as we're increasing the speed, right now we're like 1/5, 1/6 of the speed that we can go. Then becomes sixfold, right? Kind of the type of gain that we can get. So the break-even point even goes further up to 6 times.
Yeah. It's so fascinating. It's going to disrupt so many industries. Its ability to, the aviation community doesn't build that many airplanes right now, right? We just don't, in the general aviation world, we don't build that many. And so why go through the tooling, why go through the work to spend all that money when you can just punch out what you need with this?
And then if it's not successful, and then the piece is also like, so we're talking about just the production time.
Yeah.
If you're using this tool for also prototyping,
right,
then that's significantly reduced. Like, when we're working with our like aerospace partners, like, Lockheed today, we're doing a weekly basis. The traditional vendor, few months every time they make a change in their design, right? So now we're also very rapid.
It's a couple minutes.
Yeah, and we're like, okay, every week, what did you make this week? These are the things you make. They look at it and be like, okay, that design is not working out. Let's modify it. Next week, we're doing a new thing. Versus before, they need to just think about these things, a year in advance, and theoretically in their head, in their simulation, just make sure they have the right thing, right?
So we talk about how great this is. What limitations have you run across, right? I mean, we've talked about, okay, 1/4-inch steel. You've done a lot of aluminum. We've talked a little bit about the high temp alloys. What about are there any issues with super thin metals of limitations? Like, is the fidelity of these, right? Like, for example, the Zero, the old Japanese World War II, had incredibly thin skin, right? It's one of the reasons why it was so light. Do you all have issues with thin metals?
Yeah, so we've worked all the way from 0.5 millimeter all the way
half
to
a millimeter.
all the way to, I think with the newer system we can go with aluminum probably close to 1 inch, right? So we can actually go much higher than what we could do. That being said, there's always challenges with design size. You go thinner, the sheet start becoming a little bit flimsier. The stresses immediately make it to buckle and things like that. So depending on the geometry, we might have some challenges we need to work through, but that's with any manufacturing process, right? So the geometry might not kind of cooperate with you, and you might have to change the geometry, split it, do certain things to it so that it's manufacturable, but like from 0.5 millimeter up to like close to 1 inch, I think we should be able to cover.
What about on the other end of the spectrum with these alloys? We talked about a little bit earlier, but with these exotic alloys, what challenges are you seeing right now, and where are you going with that?
Yeah, so one is, as the alloy gets stronger, the our ability to push it becomes lower, so the thinner the gauge becomes, right? If you're doing a very high strength steel or titanium, you cannot really go that thick, which is not a bad thing, especially for aerospace. Usually they want thinner sheets. But also the challenge is like, the stronger usually the alloy is, the more stresses you induce in the material when you're forming it. So we need to deal with that, right? We need to figure out what are the ways through geometric design of the support structure so that we can kind of manage the amount of stresses so that it doesn't buckle or doesn't move during the forming. And those are the things that kind of the AI piece and the software piece comes into play. How can I orient the part in a way that it doesn't buckle? What process parameters do I need to use so that it doesn't buckle? So that's the active area of development to kind of widen the range of parts that we can do without facing some of these issues.
Awesome. Well, this is great. I hope that people watching this will get to look at this and see applications that they can use in whatever system they have, because I think what you've created is such a new process and such an innovative thing that you can't really see the downstream effects of how this could affect. But hopefully people watching this will say like, oh, this could apply to my industry. I could utilize this here. And so if people want to find out more information about Machina Labs, where's the best place to,
Yeah,
you know?
I think we're on major social media platforms, LinkedIn and Twitter, or X now. We also info@machinalabs.ai. If anybody wants information about our process and how we can help, just send an email to info@machinalabs.ai.
Awesome. Well, Ed, thanks for sitting down with us.
Thank you.
We really appreciate it. This was really informative. Looking
I
forward to see where
appreciate
this
it.
goes.
It's great talking to you.
All right, thanks.
All right, cheers.